Good morning, Leon. Can you hear me? Okay, good. All right. Well, this week's a busy week because we have 3 sections to cover. So I'm going to go ahead and get started. And this is the unit on linear and exponential functions. So we're going to start with section 6.6, and this is really just a review of graphing linear equations. And again, I know you took MAT 1100, so this is all going to be pretty familiar to you. So the Cartesian coordinate system looks like this, and we have 2 axes, x and y. They intersect at the origin. Horizontal is x, vertical is y. When we plot numbers, points on the graph, actually, we use ordered pairs of numbers, and they're always given in the form of a comma b. So for instance, here, if we want to plot the point 5, 3, we start at the origin. Positive numbers go to the right on the x, negative numbers to the left. So we go over 5, and then vertically, positive numbers go up, negative numbers go down. And then just a quick review here. Oh, sorry, I did it too quick. What are the coordinates of the point? So C here, you're going to start at the origin. You're going negative direction on x, and then a positive direction on y. And then point D, you're going a positive direction on x, negative direction on y. So that point is 3. And that, oh, also this is in quadrant 2. I was asking the quadrants also. This one here is going to be 3, negative 3, and it's located in quadrant number 4. Remember, the quadrants are numbered counterclockwise, rather, starting here. 1, 2, 3, 4. Okay, now we're going to talk about graphing linear equations first by plotting points. So the graph is an illustration of all the points whose coordinates satisfy the equation. And we can put equations in a couple different forms. One form is ax plus by equals c, where a and b are not 0, and these are going to be straight lines when they're graphed. And they're called linear equations in 2 variables. X and y are the variables. And since we only need 2 points to draw a line, that's really all we need to graph the linear equation, but we always suggest finding a 3rd point just to make sure that you didn't make a mistake on one of the first 2 points. And again, all 3 points on the same line means the points are collinear. So first thing you want to do when you're graphing is solve the equation for y, and then pick at least 3 values for x and find the corresponding values of y, and then plot those points. So let's look at an example. So if we wanted to graph the line, y equals 2x plus 2. The first thing we're going to do is pick some points. And let's see, we're going to find first, here we go. I've got the points already picked for us. So we're going to do x equals 0, 1, and negative 1. And so when we put 0 into the equation, 2 times 0 is 0 plus 2 gives us 2. When we put x equal 1 into the equation, 2 times 1 is 2 plus 2 gives me 4. And when I put negative 1 in, 2 times negative 1 plus 2 gives me 0. So I've got 3 ordered pairs, 0, 2, 1, 4, negative 1, 0, and I can graph those points. And here they are on the line. And it turns out, actually, this first point is the y-intercept, and the last point is the x-intercept. Now you can also graph just using the intercepts. So the point where the line crosses the x-axis is the x-intercept. Let's just get back for a second. On this example, here's the x-intercept, the point where the line crosses the x-axis. The y-intercept is the point where the line crosses the y-axis. So to do the intercepts, it's easier to leave it in, this is called standard form for a linear equation. It's better to leave it in this form than to solve for y like we did in the prior example, because you'll see when I go ahead to find the intercepts, to find the x-intercept, we set y equal to 0 and solve for x. And so when it's in the standard form, what happens is the other term just drops out. So we've got 2x equal to 6, so x is 3. So the x-intercept for this is 3, 0. And then to find the y-intercept, we're going to let x equal 0. And again, this term's going to drop out. And so we come up with y equal 2. So the intercept here is the y-intercept rather is 0, 2. And once I have the 2 intercepts, I can graph the equation. And we'll do a checkpoint here just to make sure we have a 3rd point. So we'll let x equal negative 3. So I put negative 3 into the original equation. That was 2x plus 3y equals 6. I get negative 6 plus 3y is 6. Add the 6. 3y is 12, so y is 4. So the third point I have is negative 3, 4. So here's my graph. So here's my x-intercept, here's my y-intercept, and there's my checkpoint, and I see that they fall right on a nice straight line. Now, the slope of the line, again, we studied this in MAT 1100. The slope of the line is a measure of the steepness of the line. And it's the ratio of the vertical change. So if we remember the Cartesian coordinate system, and it's the slope is the ratio of the vertical change, the change in y, over the change in x. And we can use any 2 points on the line to find the slope. Vertical change over horizontal, y2 minus y1 divided by x2 minus x1, using any 2 points on the line. It's also sometimes written like this. The change in y, delta, this is the Greek letter delta, means change, so the change in y divided by the change in x. So just a couple of examples. Positive slope, as x increases, y increases, so the line will look like this. Negative slope, as x increases, y decreases. Okay, a horizontal line has a 0 slope. Everywhere along the line, y equals some number. And a vertical line has no slope. It's undefined. I shouldn't say no slope. The slope is undefined. So let's try an example to find the slope of the line that connects 2 points. So we have negative 1, negative 3, and 1, 5. And I'm going to go ahead and specify this point is point 2 and this is point 1. So y2 minus y1 over x2 minus x1. And then I'm going to go ahead and simplify the numerator and denominator. So I've got 5 plus 3 is 8 over 2, or 4. So the slope of the line that connects those 2 points is 4. And the slope of 4 means there is a vertical change for each vertical change of 4 units for each horizontal change of 1 unit. And the slope is positive, so the line rises from going from left to right. And here's what it looks like. Here's the line, and those are the points that we used. Now remember, the slope was 4. So if I move from this point here, this is the y-intercept. X increases by 1, y increases by 4. So if I go from this point to the next point, x increases by 1, y increases by 4. And that's what they're showing you over here on this graph. So you can actually read the slope right off of the line. And again, we covered that in MAT 1100. It's a nice skill to have, is to be able to read the slope from the line. Or you can also use one of the intercepts in the slope to graph the line. Now the other form of the line, if you remember just a minute ago, we had the form up here of ax plus by equals c, and we called that standard form. This is what we call the slope-intercept form. So you can always take the standard form and rewrite it. And in slope-intercept, we see y equals mx plus b, where m is the slope, and 0b is the y-intercept. So this is a nice form to have the linear equation in, because we can simply read the slope and the y-intercept right from the line. And again, I mentioned we can graph using simply the slope and the y-intercept. So to do that, you want to solve for y, put it in slope-intercept form, find the slope and the y-intercept from the equation, and then plot the y-intercept, and then use the slope to find a second point. So let's take an example here. So we want to write 4x minus 3y equals 9 first in slope-intercept, and then we're going to graph it. Okay, so here's the solution here. So 4x minus 3y, the first thing we did was we want to get y by itself. So I went ahead and subtracted 4x from both sides. And so on the, get my pencil here, over here, these are going to cross out, going to cancel. And then I've got negative 3y over negative 3, divide both sides by negative 3. And so I end up with y, negative 3 cancel. And then I end up with negative 4 over negative 3 gives me positive 4/3 x minus 3. So here's my slope, and my y-intercept is 0, negative 3. So to graph it, I graph the y-intercept, 0, negative 3. And then, remember, my slope is 4 over 3. So it means x goes up by 4, y increases by 3. So here's the next point on the line. And I can actually check that point. The coordinates of that are 3, 1. and I could put that back into my equation and check and make sure that it's true. So if I put in x equals 3, let's go ahead and do it. Y equals, whoops. So I have 4/3, and I'm going to substitute in a 3 for x minus 3. So what happens here, I've got the 3's will cancel. So 4 minus 3 equals 1. And that's the point that I had right here. 1, 2, 3, 1. And so that satisfies the equation. So it's nice to check, especially when you're using this method to graph, that you didn't make a mistake when you applied the slope to find another point on the line. So go ahead and confirm that point. Makes a true statement in the original equation. Okay, and now this time we're going to go the other way. We're going to give you a graph, and we're going to say, what's the equation of the line? All right, so I can tell by looking at the line, I can tell the y-intercept, right? It's 0, 1. So that part's easy. Now, next thing we want to do is find a slope. So if we notice the form of the line, is it going to have a positive slope or a negative slope, Leon? Because that gives me some hint of the kind of answer. It's going to have a negative slope, right? So if I think about moving from this point to this point, x increases by 3, but y decreases by 1. So the slope is going to be negative 1/3. Okay, so to go from this point to this point, x is going up by 3, but y is going down by negative 1. So the slope is negative 1/3. So the equation of the line is going to be y equals negative 1/3 x plus 1. So there's my equation of the line. So you can go both ways now. You can take an equation like this and graph the line using just that equation, and then you can also look at a graph and give us the equation of the line. Now this is only true with a linear function, obviously, not with anything else. And then lastly, just the two horizontals and verticals. So we want to graph the line y equals 2 and x equals negative 3. So if you remember, the y equals were horizontal lines. So that's what that would look like. And then the x equals are the vertical lines. And again, remember, let's go back just for a minute. On this one, the slope is 0 on the horizontals, and on the verticals, the slope is undefined. All right, and then let's just finish up with a little definition on this section, the dependent and independent variables. And again, we did go over this in the MAT 1100 class. When we're graphing equations, and it's especially going to be true when we get to the regression section in a minute. We label the horizontal as x and the vertical as y, and for each equation we determine the values for y by substituting for x, which we just went over. Since the value of y depends on the value of x, we call the y the dependent variable and x the independent variable. And we're going to go ahead and always label the vertical axis with the dependent and the horizontal with the independent. And remember, in some applications, we don't have x and y. We may have variable labels that match the problem. So x and y are kind of the generics, but a lot of times we'll use other labels for the two variables. But always on the horizontal is going to be the independent, and on the vertical is going to be the dependent variable. Okay, so let's go ahead and skip up to 6.10. So we just did the linears. Now in 6.10 we're going to expand this a little bit more, and we're going to look at linear and also exponential functions. And we're going to talk here about relations and functions. So a relation is any ordered pair of numbers. There's some kind of an association between the x's and the y's. A function is a special kind of a relation where every value of the independent variable corresponds to a unique value of the dependent variable. And the domain is a set of values used for the independent, and the range is a set of values for the dependent. And so just to give you, there's an example in your book, I'm not going to go over here, but they're looking at a function like this. The equation says it's the cost. It's the cost of some product, and each product is $1.29. So we multiply the product price times the number we sold to get the total cost. So the domain here are the n values. What values can I put in here for the number of items? And then that's what we call the input also. And then the output here is going to be the cost in this example. So if I buy one product, I pay nothing. If I buy no product, I pay nothing. If I buy one, I pay $1.29 and so forth. So the mapping occurs so that from the domain, it maps onto only one and only one value in the range. Now, in the range, multiple values from the domain can be mapped, but not the other way. So let's take a look now at a way to determine from a graph if we have a function. If a vertical line can be drawn so that it crosses the graph at more than one point, then x does not have a unique y and it wouldn't be a function. So if you notice here, this is a parabola, which we're not going to go over in this section, but if I drop a vertical line here, it only crosses the graph at one place. So that tells me that that's a function. And we call this the vertical line test. So let's try a couple examples. So here's one here. Determine if the graph represents a function, and if it does, what's the domain and the range? So again, what do? We use that vertical line test. We drop the vertical line down, and if you notice here, when x is -2, y might be 1 or it might be -1. So it's not a function. Is it? Oh, I'm sorry. Oh, geez. Yeah, basically the vertical line test is going to, let me show you the next one so you get an idea, the comparison. So if you look at this one, Leon, now when I drop a vertical line here, this is a function because the vertical line only crosses in one place. So it tells me in this case when x is around 3, my y value is right here on the graph. But there's only one output value. On this graph here, if I go to x equals -2, I could either go to +1 or I could go to -1. So this is not a function. I don't get a unique y for each value of x. Okay. Now, but notice on the y side, you don't do it horizontally because you can use the y values more than once. It's the x uniqueness that defines the function. Now let's do the domain and the range on this one. So if you remember, domain is x. What values of x could we use or does this graph define? So look along the horizontal axis and we see that x is going from about 0 up to, I think that's 8, right? 2, 4, 6, 8. Yeah, 0 to 8. And then the range goes this way. So now you look to see what's the smallest value that y takes on in this graph, and it goes from about -1 to +1. Okay, does that make sense, Leon? Do you see the difference between the domain and the range? A lot of students have trouble. Domain means you look this way. So what values of x can I put into this function to get an output? And then y goes this way. Yeah, you're right, because a lot of the ones, when we get to the exponentials in a minute, we have a lot of domain and ranges that go to infinity. You're right. Yeah, this one stops, though. You notice the graph? Okay, if we were trying to, we don't actually do a domain and range if it's not a function, but if you look here in the y direction on this graph here, this would, if there was a little arrow here, it would say it would keep going and going, so then you would have an infinity, positive, and negative infinity. But you're right, a lot of the times they're going to have infinity in the ranges. Okay, so we already just did the linear, so this should just be a review here. The other thing we can do when we're talking about functions is we change the y to say f of x because we're talking about a function of x. So we're saying that the y is actually the function evaluated at that particular value of x. So f of 1, f of 2, whatever we happen to be doing. It's nothing different in terms of what we graph. The same thing, to evaluate the function, we substitute the given value and determine f of that value for x. So for instance, if I have this function, f of x equals -4 plus 7, evaluate it when x equals 3 and also when x equals -2. So I'm going to get two answers. So for f of 3, so you see what's nice here is the terminology shows you what you're doing. So everywhere I see x, I'm going to put in 3. So I'm going to get -12 plus 7 is going to give me -5. And then I'm going to evaluate f of -2. Put in a -2 for x, so I get 8 plus 7, and I get 15. So this is just like evaluating that we did again in the 1100 class, but we're just using the functional terminology. Okay. Now we already did the graph, so again this should be pretty much of a review. The graphs of the linear functions are straight lines, and these will pass the vertical line test except for a vertical line. And they're graphed by plotting points using intercepts or the slope and the y-intercept. So we just went through that in the first section. So graph this function using the slope and the y-intercept. So again, from the equation we can see, so f of x is y, so we can write this like this. The slope is going to be -1. The y-intercept is 0, -1. I can tell that from the equation. So we can plot the intercept and then use the slope to find a second point. And again, because the slope is negative, we know the line is going to be decreasing as x increases. So I plotted the y-intercept, which was 0, -1, and then I'm going to use the slope of -1 to get some more points. So I could go x increases by 1, y decreases by 1. X increases by 1, y decreases by 1. So there's another point on the line, and there's my line. So again, we just did that in section 6.6, so this should just be a review. Here's another one, graph using the slope and the y-intercept. So the slope here is -2, the y-intercept is 0, 3. So I plot 0, 3, and then I'm going to use my slope. As x goes up by 1, y goes down by 2. X goes up by 1, y goes down by 2, and I've actually now got 3 points on the line and I can graph it. And again, you may want to check these points, like this is 2, -1. Make sure that makes sense in the original equation. And we're going to actually do an evaluation. So let's find f of x when x is 0. So I substitute in 0, and then I get that's my y-intercept, 0, 3. And then let's do f of -1. So that would be right here. F of -1. And I get +5. And notice that's on the graph. 1, -1, +5. Okay, let's try an application in here. We didn't do applications in 6.6, so we'll do 1 or 2 in here. All right, so Marta, is part owner of a newly opened candy company. The annual profit is given by this function, p of x equals 3.5x minus 15,000, where x is the number of pounds of candy sold per year. If Marta sells 20,000 pounds of candy this year, determine her profit. So we're going to take the function and we're going to evaluate it when x is 20,000. So the profit of selling 20,000 units is equal to 3.5 times the 20,000 minus the 15,000. And so her profit's going to be $55,000. So if she sells 20,000 pounds of candy, she will make a profit of $55,000. All right, and I think you have something similar to this in the homework, where they'll give you the function and then they'll ask you to evaluate. All right, so now let's go to exponential functions. And if you remember, Leon, we did cover these in the MAT 1100 class. So an exponential function, many real-world problems can be modeled using an exponential function. It means things are growing or increasing or decreasing rapidly. Okay, in a linear, for every unit of change, the relationship changes by a fixed amount, which is the slope. Exponential means we've got a rapid rate of growth. So we've got exponential growth, or we've got exponential decay. So growth means increasing, decay means decreasing. One form of an exponential could be written like this, y equals a to the x, or again we can use the functional notation, f of x equals a to the x. In both cases, a is going to be positive and a is not going to be equal to 1. And then the value of x is going to determine whether it's increasing or decreasing. So here's an exponential function on population. So as the years go by, the population is increasing exponentially. We see that curved line there. So here's the basic form, and again, we went over this in MAT 1100. So let's go through the definitions here. Here's the basic form. P naught is the original amount present. So if you think of a population, the initial number of people, or if you think of radioactivity, the initial amount of the compound. And then P of T is the amount that's present after T years, and A and K are constants. We just said A is greater than 0, and it's not equal to 1. And then depending on what the exponent is going to tell us if it's increasing or decreasing. So if K is greater than 0, A is greater than 1, we have an increasing function. And if k is less than 0, a is still greater than 1, it's going to be a decreasing function. Now, one special kind of exponential is called the natural log or natural exponential function, where the a is replaced with what we call base e, which is a base that appears in, oh sorry, my phone's ringing. Let me just mute for a second. Okay, Leon, sorry, it stopped ringing there. Sorry about that. The natural log function, I don't know if you've ever heard of the natural log function, but it appears in a lot of places, especially in science. And you should have a key on your calculator, an E key. Okay, yeah, it's new. Okay. It's used in mostly in science, I would say, but sometimes in business too, in the way that we define some of the ways that business operations grow. If you look on your calculator and you push the key, so if you push in e to the 1 power, let's say, you can get a look at, you had to dig it out, okay. Yeah, if you push that key, if you find that key, it's usually a second function key related to an ln. If you put it in and raise it to the 1 power, you'll see that, let me just write this up here, the base e is approximately, here's an approximate sign here. It's 2.718. I don't know if I put it on any of the slides. Oh, I have it coming up in a minute. I do, actually. It's about 2.718. But it's a base that we use. Whoops. I don't know why that went so fast there. Okay, there's only one thing on the slide. Here's where it changes, though. It's the same form. The only difference here is the base changes. Everything else is the same in terms of the general form of the exponential function. It's just instead of an a here, we're going to have the base e when we have an exponential function. And it's an irrational number called the natural base, whose value is approximately 2.7183, and it keeps going and going and going. Irrational. So it's a non-repeating but infinite decimal. And it's really important in mathematics and also, like I said, in science and also in some business applications, because I know there are some business functions that use a base E. So let's just take a look at how a problem would be worked. So let's look at plutonium as a radioactive material used in most nuclear reactors. Decays exponentially at this rate. Notice this is a percent too. If there are originally 2,000 grams of plutonium, the amount of plutonium remaining after T years is given by this function. Now they'll give you the function. So if you notice here, here's the initial amount, here's the base E, and it's a negative exponent, which means it's going to be decreasing, and they took this and put it into the decimal 0.003%, and they put it in as a decimal 0.00003 times time. How much plutonium will remain after 50 years? So you're going to substitute in the formula for T 50. So again, you're going to have to find on your calculator where that base E is. And then be careful again, this is a negative exponent. So you want to make sure you catch that when you're doing the exponent. And the first thing I did was multiply the negative 0.00003 times 50. Then I'm going to put in the base E and raise it to that power. And I got approximately 0.9985. And then I'm going to multiply by 2,000. And this one actually, I believe it said on this one to round to the nearest gram. Let me just look at my notes over here. Oh, I didn't give you instructions. I think in my math lab they have you rounding on one like this to the nearest gram. So this would be 997 grams are remaining after 50 years. So if you think about this in the context, this is plutonium. You start it with 2,000 grams. After 50 years, you still have almost 99% of it left. So this is a very slow exponential decay when we're talking about this radioactive compound plutonium. All right, so let's do a little graphing on this. And you're not going to actually graph in your homework. You're going to identify the graph. So we want to graph the function y equals 2 to the x, and then we want to find the domain and the range. So the same thing we did before is we pick some values. I should have brought the function over here too. What do we do? We were doing y equals 2 to the x. Okay. Let me just type it up here. So we're graphing y equals 2 to the x. There's what we're graphing. And I picked some x values, and I went ahead and did them on paper and pencil. You can do them in your calculator also. But when you put in a -3 here, when x is -3, it's y equals 2 to the -3, which is 1/8. Put in -2, you get 1/4, and so forth. And so if you notice here, as x is increasing, y is increasing. So we have a general idea of what the graph is going to look like. So here's the graph. So look at the points. -3, 1/8 is pretty close to the x-axis, and then -1 was 1/4. I'm sorry, -1 was 1/2. -2 was 1/4. The y-intercept here is 0, 1. And then we had a 1, 2, a 2, 4, a 3, 8, and then we just connect the dots like that. So again, in your homework, you're not going to be doing it by hand. You're going to be picking the correct graph. So the first thing I would do is look at whether or not as x increases, y increases or decreases, because generally of the 4 choices, you're going to be able to eliminate one of them. And then you want to go ahead and take a look at your points. All right, so let's look at the domain and the range, and I'm going to keep the graph up here. So domain means the x values. So Leon, what x values can this function take on? And if you notice on the graph here, there's a little arrow on either end of the curve. So that means it keeps going and going and going. Yeah, any, right. And this is where they're going to write it as all real numbers, or, so it might be written, I don't remember the answers in my math lab, so it could be written as all real numbers, or it might be written as negative, and I'll bet you don't have a letter for this. Let me see if I have a letter. Oh, here I do. Negative infinity, less than x, less than positive infinity. So these are 2 ways to say it could be any number, and I'm not sure in the answer possibilities in my math lab which one they use, but these are saying the same thing. Okay. All right, so let's look on y now. Y is in this direction. Now if I notice, the graph is entirely above the x-axis. So what does that tell me about y? It's never going to be negative. Right, and it's not ever going to be 0, because if you notice, this is never ever going to go across that x-axis. So when we talk about the range here, so the range is going to be, y is going to be strictly greater than 0. Okay, so does that make sense? That was where the domain and range came in. And I'm thinking on almost everything you're going to do in exponentials, the range is always going to be all real numbers. I'm sorry, the domain. The range may change depending on where the graph falls, because sometimes they're above or below the x-axis. Okay, does that make sense? Okay, good. All right. So, last section. I know we got a lot of stuff this week. So this is your big hump week, so to speak. Yeah, it was a busy week, I know. After this will be 2 sections a week. The hard thing with spring semester is the midterm comes a week later than it does in the fall, and so we end up having to push more stuff in after the midterm for students. So it's not a good thing, I know, but and it's more logical to keep material together that goes together. Yeah, I know. I wish you would tell the higher-ups at the college. We've been arguing this for a long time. We would prefer you to have the midterm before the spring break. I think it would make a lot more sense, but it falls on deaf ears. So anyway, yeah, faculty have been lobbying for that for a long time, but it's never changed. But anyway, this will be the worst week, I promise you. But the 3 sections go together, so that's why I think it makes sense to put these 3 together. So now we're going to do linear correlation and regression. And this again goes along with, and again, it's linear. Okay, so it kind of all goes together here. So I'm going to jump through this part real quick. All right, so correlation is used to determine whether there is a linear relationship between 2 variables and how strong it is. And regression is how we determine the line that best fits the data. These problems are too long, okay. All right, well, all right, linear correlation coefficient. We use the letter R, It's a unitless measure that describes the strength of the relationship between the two variables, and the relationship has to be linear. So it's really important that you make a graph before you calculate the correlation coefficient. If the value is positive, then one variable increases and the other variable also increases. So you think about a line with a positive slope. If the correlation is negative, then one variable, as it increases, the other one decreases. So the correlation coefficient R is always going to be between -1 and +1, and it doesn't have any units. It's independent of the units that the variables are measured in. So the visual aid, again, we went over this in MAT 1100, is called a scatter diagram or a scatter plot. So we plot the points on a graph, we don't connect them, and we make a picture. And X is the independent variable, generally the variable that can be controlled or helps us to explain the Y variable, which is the dependent variable. And the value of R is a measure of how far a set of points varies from a straight line. The greater the spread, the weaker the correlation, and the closer R will be to 0. The smaller the spread, the stronger the correlation, and the closer the R value is to 1 or -1. So here's a couple pictures. Now again, notice we don't connect the points. So here's one which has got perfect correlation. These, if I were to draw a line here, it would connect all those points perfectly, a straight line. R equals 1, strongest positive correlation. This is still positive, but not as strong as this one was. This is still positive, but less positive, less strong. It's weaker. And then this is no correlation. As X is increasing, Y's could be doing anything. So there's no relationship here. And do I have negative ones? Oh, I do. Here we go. Positive. This is a perfect negative, so this will be R equal -1. This is still pretty strong, so this might be -0.9. This is a little bit weaker, maybe -0.4, 0.5. And then this is no correlation, no association. And if you were to do a correlation on a set of points like this, you'll get a correlation close to 0. Likewise, let me just flip back for a minute. If you did a correlation on this set of points, you'd also get an R value close to 0. All right, so here's the formula. Don't panic. We're not going to do things by hand. I'm going to have you, either you'll be given it, or there's also, I think you have 1 or 2 problems in your homework where they actually ask you to do it. And I'm going to suggest that you use Excel. And I have a video for you in the module, Unit 3 module in my courses that shows you how to use Excel. Oh, you did it by hand. Okay, well, Excel is really much better to do. You can do it by hand, but it's a lot of work, as you probably found out. So let me see. I think maybe I do one by hand here. Oh, yeah, and I actually have screenshots coming up for Excel. Yeah, I do this one by hand. So this is daily records about the number of assembly workers who were absent and the number of defective parts produced for 6 days. Determine the correlation between the number of workers absent and the number of defective parts produced. So here's the data. And we did not do it. Oh, actually we do. We're going to do a scatter plot in a minute. So here's the day, and then here's the number of workers absent, and here's the defective parts. And so we might think as the number of workers absent increases, we get more defective parts. That would kind of seem pretty logical. Too quick, sorry. So here's the scatter plot. And we would think, again, the number of workers absent would affect the defective parts, so therefore I put workers on X and the defective parts on Y. And I do see a linear trend there. As the workers increase, the parts defective increase rather. All right, so if you're going to do it by hand, you have to make up this little table here. And you need to create a column, put the X in, the Y, add up the X's, add up the Y's, square the X's here, add them up, square the Y's, add them up, and then take what we call the cross product, X times Y, add those up. And then these are the 5 numbers down here that you're going to plop into the formula for the correlation coefficient. So you notice here's the sum of the cross products, the sum of the X's, the sum of the Y's, sample size. In our case, the sample size was 6, sum of the X squareds, sum of X quantity squared, and so forth. And so in this problem, when I plop the numbers in and go through all the simplifications, we end up with a correlation of 0.922. Now remember, it has to be between -1 and 1. So if you get a number outside of that range, something's wrong with your calculations. Since the maximum for R is 1, this is a very strong positive correlation. It implies that generally the more assembly line workers absent, the more defective parts produced, which makes sense. So to use Excel, and again I've got a video in the unit module in there in my courses for you. So enter the values into Excel. So I put in the absent workers here, defective parts here. Click on an empty cell, type an equal sign, and then in the function window up here, you want to click it open. I don't have the pull down menu, but all the way at the bottom there's a search function, and you want to search for the function CORREL. And then you identify the first array, the first column, the second column, and then you just hit OK, and you get your correlation. And that's the same number that we got when we did it by hand. So it's a lot quicker, obviously, to do it using Excel. And if you remember, you get Excel free at the college. If you go into My SPC, there's a place there where students can download the whole Microsoft package. I think there's also Excel in Google Docs, somebody told me too. I don't use Google Docs, but no, on the final, Leon, I won't have you do a calculation like this. I promise I won't, because the proctors don't like you opening other screens up. So no, I'll give you some problems on interpretation, or in a minute we're going to test if it's significant or not, and you'll do that, which is easy to do. We use a table for that. Yeah, no, you're not going to open up Excel. Definitely not. All right, so, and there's the correlation. All right, so now we know there's a strong positive. Now, what if the correlation had been 0.53? Would we be as impressed? And so this is where we come up with a way to test. Yeah, we wouldn't have been, right? And there's a table of significant values for the correlation, and I put it up here. You've got it in the handout, and it's also, I think it's always in the problems when they ask you for it. So you go down here with the number of samples you have. So we had 6 this time. And if our correlation was 0.811 or higher, it would be significant at what we call the 0.05. And if it was 0.917, it would be even more significant, which is where we were. We were right here. And we had 0.9, what do we have? 0.933, right? Yeah, so ours is highly significant. So let me go back and show you. Okay, so there's the table. So we're going to look for n equals 6, and we got 0.922, and ours is more extreme than this value here. So therefore, we say that we have a highly significant relationship. So this is significant at the 5%, and it's also significant at the 0.01%. And again, this is the kind of thing I'll ask you on the final exam. I won't ask you to do calculations. You're doing that now with your homework, so that's good enough. And then I just put up here, because in the homework I did give you some problems like this where they tell you the correlation and they say, is it significant or not? So for instance, n equals 6 and alpha is 0.05, and our correlation was negative 0.92. So we go down to 6, and they want it at the 0.05, and this one is, remember we use the absolute value. So it would be more extreme than the value in the table, so this would be significant. How about when n is 10, alpha of 0.01, it would have to be more extreme than 0.765, and this correlation was negative 0.49, so it's not significant linear correlation. How about when n is 7, and we got 0.77, and we did it at 0.1, it wouldn't be significant. If we had done it at 0.5, notice this one would have been significant, but they asked us to test it at 0.01. And again, there's the other one. So it is significant at 0.05, but not at 0.01. So you have some homework problems like that. And I think I only gave you 1 and 2 where you have to actually, 1 or 2, to actually calculate the correlation. Oh, hold on for a minute. My slides are stuck. There we go. Okay, so last thing in here, linear regression, which goes along with the correlation. This is how we fit the line, or create the line that fits the data the best. Okay, and it's called the line of best fit. It's the line such that the sums of the squares of the vertical distances from the line to the data are minimized. And we want to get an equation like this, y equals mx plus b. Now, if you notice, it's using the same quantities that you used when you did the correlation. But again, I'm going to suggest using Excel. It's a whole lot easier. But we're going to find the slope, and you're also going to find the y-intercept. And what happens is, let's see if I have a graph here. Oh yeah, we're going to do it on the one we did before. The workers, the assembly workers, and the defective parts. So we're going to find the equation that fits the line the best, and then we're going to graph it. So again, if you use the formula by hand, here's the formula for the slope. And for this example, it comes out to be about 3.23. And then you're going to do the y-intercept. And for this problem, it comes out to be about 8.52. So here's my equation. Now, again, in Excel, let me show you this real quick in Excel, how to do it. I've got the data in there already. If you remember, we put it in before. Here's my workers and my defective parts. Pick an empty cell, type an equal sign, and then search for the function LINEST. Now, this one's a little trickier because you've got to look here to pick up the equation. It doesn't, because it gives you two values. You're going to put in the y's and the x's. And then if you notice here, the first number that comes out is the slope, and the second number is the y-intercept. And you have to write this down, Leon, because it doesn't store both numbers in that cell where you type the equal sign. It's a little strange, this one. It doesn't come out the same way. So again, here's your slope and your y-intercept. And again, you're going to get the same thing. So there was the equation, y equals 3.23x plus 8.52. And we want to predict the number of defective parts when we have 2, 4, and 6 workers absent. And let me just see, because I had a mistake on my slide. No, I fixed it. Okay, so when 2 workers are absent, what do we predict for the number of defective parts? So we're going to substitute x equal to 2 into the equation, and we get a prediction of about 15 parts defective. When 4 workers are absent, we're going to predict about 21 and a half parts defective. And when 6 workers are absent, we're going to predict almost 28 defective parts. And then the last thing I wanted to do was graph it. So I'm going to use those 4 points to graph the line. And I'm also going to show the line. Here's the fitted line right here. Here's the actual data values. And so this line was fitted such that the distance from the actual data points to the line is minimized. So if you notice, this point is actually on the line. This point's pretty close. So is this one. These are a little further apart. The other interesting thing, which your book doesn't stress, but the way the line actually gets fitted, it's fitted into, it always crosses the mean of the x's. It's cemented onto the graph basically at x, the mean of the x's and the mean of the y's. And then it's basically rotated mathematically so that the distance from the points is minimized. And again, if you go into Excel to create the scatter plot, you've got your data values in there. You want to go to Insert, and you want to scatter plot simple. Select the data. And then here's your scatter plot coming out of Excel. And there's also an option to add the, if you select design, you can actually add the linear regression and the equation. So select chart element and add the trend line. It's called trend line in Excel. And I think, I didn't show it here, I think there's also, hold on a second, there's also an option to actually add the equation. I didn't show you that, but there is an option where you can actually add the equation. No, I didn't show you that. I think it's in the video though. Okay. All right, so Leon, a lot of stuff this week. It's the longest chat I think we've ever had, but 3 sections. I know it's a lot, but it all kind of goes together. It really does. And again, try to use Excel because I think it's nice because if you ever in your job need to do a regression or a correlation, you'll be familiar with it. And again, I don't know, you're taking 1106 now. Are they using Excel at all in there for the statistics? Oh, you're not up there yet, are you? Did you do statistics already in there? Okay, I think it's the last unit. So they might, but that's another thing when you get into statistics in the 1106 course. Think about Excel because it's pretty easy to do means and so forth in there. Okay, Leon, any questions? I know it was a lot of stuff this week, a lot of stuff. Okay, no, I know it's a lot. Like I said, because of the midterm being a week later in spring, it's always hard to dice up the material so that, there's not too much any one week. But this is the worst week, I promise. After this, it'll be 2 sections a week. We're almost done, actually. And I know you're graduating, so it's going to be a busy semester for you. Yay. All right, Leon. Well, if you're good, I'm going to sign off. And again, next week, I promise, only 2 sections. It'll be a lot calmer. So have a good week, okay? And we'll chat again next week, Leon. Bye.